The meaning of the integral, which I've kind of drilled into you, the meaning of an integral is the area. And so far, you've had two ways to find area. You've used geometry to find area, or you've used Math 9 to find area. Today, we're going to talk about how to use calculus to find area. So we've been studying kind of for the last week, building up to this point. We're going to be doing this with the concept of an antiderivative. So we needed to kind of review our derivative rules so that we could be good on going the opposite direction. So for one last time, this is one kind of rule we did not review. Let's find the following derivatives for these three functions. All right, so Tyler, since you didn't get to do any of the other ones, what is f prime? 3x squared, good job. All right, and Nathan Deere, since you didn't get to do any of the other ones, what is g prime? 3x squared. Okay, and Isaac, you were left out as well. So what is h prime?
3x squared.
Okay.
Yay!
So we call this a family, a function family. These are all cubics. What's the difference in the three original cubic functions? The y-intercept. All of them have been shifted somewhere different. One of them's been shifted up 7, one of them's been shifted down 5, one of them's been shifted up pi, but they all have the same derivative, and we know that the derivative means what?
Same slope.
Same slope. They all have the same slope. So they all are curving in the same way. Okay? They all are considered. The only difference is the plus or minus whatever on the end. We generalize this, and we call this plus or minus capital C. We call that a constant. That if the only difference between several functions is their constant, if everything else is the same, then they will all have the same derivative, which means they have the same slope. What do we call two lines that have the same slope? We do. We call them parallel. Is it possible for two curves to be parallel? Because what do two parallel lines never do? Never touch each other. Is it possible for two curves that are parallel to never intersect each other? For sure. Okay, they're just going along. Okay, they're curved, but they never will intersect each other. All right, so notation-wise, if f of x is a function, we've decided and we've all agreed that f prime of x is the derivative. But how do we say when you want the antiderivative? Okay, and if you want the antiderivative, you're going to use capital F of x. Any capital letter is the antiderivative. Okay, I usually kind of make it a little bold, emphasize, but we want a capital. That's our notation. So that's when I say find capital F, now you are thinking, oh, okay, now I know what she wants me to find as opposed to finding f prime. Okay. Starting in the center, if the function is x cubed, we just now agreed that the derivative is always going to be 3x squared. Notice the difference in the powers. A cube becomes a square when you do a derivative. What will the cube become when you do the antiderivative? A fourth. We call that a quartic. Okay, so a cube will become a fourth power. All right, so it is the fourth power. Now, is that all it is? What would the derivative of x to the fourth be? It would be 4x cubed. And we just want it to be plain x cubed. So how are we going to make it be plain x cubed instead of 4x cubed? Make it a fraction. What do you mean?
Make it so that it be equal to 1. Like, yeah.
Okay, how do I do that?
Change it to 1/4.
Change it to 1/4 of x to the fourth. That's called the antiderivative. The antiderivative has a different power. The power is 1 higher, and it has a different coefficient so that the coefficient will cancel out with that power. You also have to remember to put plus or minus c on the end because there could be a constant there that when you take the derivative would disappear. You don't always have to put the minus. You could just put plus c because c could be a negative number and that's fine as well. So plus c would just be fine. If you want to do plus or minus c, that's okay. It doesn't matter, but plus c is fine. Okay, let's try another one. So we start with 5x to the fourth. Our derivative is going to decrease, and it will be down to x to the third, but what will be the coefficient there? 20. How do we get the 20? We have multiplied, okay? Multiplication. All right, so let's do the antiderivative. What will the new power be? Okay, that coefficient of the 5 is still there. The new power is still there, but now I have to divide by the new power. And so what happens to the ultimately to those two things? They reduce. And then I remember to put a plus c. That would be commandment number 6 that I would remember, or that I would say, thou shalt not forget plus c every time you do an antiderivative. Okay, it is that important.
Is it plus or minus c?
It does not matter to me. You may do plus or minus, but it's more common to just see plus c.
I know that's
Okay, so let's see if we can summarize this rule. In a derivative, we say, bring the power to the front, multiply, and then minus 1 to the power. Okay, that's what we would say. Bring power to front and multiply. Subtract 1 from power. That's the order. Step 1, step 2. If you were going to do the antiderivative, can you come up with a rule for me that is the exact reverse of that? Okay? So, I mean, like literally the exact reverse. So, step 2 would become step 1. So, step 1 would say add 1 to power. That's the opposite from subtracting 1 from the power, and it becomes the, and then what would step 2 be? Bring power to where? Not to the back,
to the up.
to the denominator, okay? Bring power to the bottom.
Bring it to the bottom.
Got it, thanks. Oh, hello. Bring power to bottom. And instead of multiply, what do? Divide. That's your rule for an antiderivative. Add 1 to the power and bring that power to the bottom and divide. That will work for every single antiderivative that you do. Okay, let's see if these rules will apply. So let's do a derivative first. So where do we bring the power for our derivative? To the front. And then what do we do to the power? We subtract. All right, for an antiderivative, we keep, excuse me.
It's just one.
Oh, I'm sorry. Positive 1. For an antiderivative, we're going to reverse that. So what is the new power? 5 over 2. So increase the power by 1 and bring the power to the denominator and divide. And then what else do we have to remember? Plus c. So that looks a little awkward, so it's better to write 2/5, because remember dividing by that fraction is the same as multiplying by the reciprocal. So you want to do that instead and then add c. So I would write 2/5 to x to the 5/2 plus c. You don't have to make that into a square root. It is a square root, but you don't have to make it into square root. You can simply leave it like that. What do you need? All right. Okay. Let's see if we can do it twice. Now, you don't want things to be square roots when you're doing this. You want them to be in powers. So the first thing you would want to do is change this to x to what power? Okay. Okay, so let's do the first antiderivative. So if it's starting as dy dx with lowercase y, dy dx, what will the next step up in its antiderivative be? No, just the, like what goes over here? Not f of x, we're not using f of x this time. What are we using? Y, lowercase y. Okay, because I was dy dx, now I'm going to regular y. Let's find our new antiderivative. So x becomes what power? 3 over 2, and then I take that new power and I divide by 3 over 2. So the best way to write that would be 2 over 3, x to the 3 over 2, plus some capital constant of c. Let's do it again. If I'm going from lowercase y, then what is its antiderivative? Uppercase y. Okay. What do I do with the 2/3? Nothing. 2/3 x. The only thing I'm doing something to is to the power. And so it will be 2/3 x to the new power being 5 over 2. And what do I have to do with the 5 over 2? Divide by 5 over 2 plus, not 2c. Okay. Why? Okay, c represents what? A constant. Give me an example of a constant. 4. Sure. Okay. What is the antiderivative of 4? Well, 4 is just a constant. Where would it have come from? It would have come from 4x. Okay, so c comes from, but I need a new constant added on to that. Because every time you do an antiderivative, you gain a new constant. So call the new constant capital D or whatever. It's just a new constant. Or you can call it C1 and C2 if you want. Doesn't matter. All right. Let's keep, we're just practicing. Now in the last example, you saw me change the radical so that it was a power. I want to change this as well so that it's a power. You always want things to be powers before you do their antiderivatives. Okay? So I want to change this to be 3 instead of divided by x squared. I want it to be 3 times x to the negative 2. I want it to be that way. Okay, I need a volunteer. Okay, Tyler, do you want to do the derivative or the antiderivative? Okay, he's going to do the derivative.
Okay, negative 6x to the negative.
Okay, and when you're done, you would change that back to negative 6 over x cubed. But that would only be when you're finished. Okay, now I need a volunteer to do the antiderivative. Okay, Andre?
Negative 3x to negative first.
Okay, what do I do with that 3 that's there?
Oh, you should keep.
I just keep it. So this becomes 3 and then x. All right, now I have to decide what the new power is.
Negative 1.
-1. And then what do I do with that -1?
Divide by -1.
Divide by -1. And then I'll have a plus c. So then when I'm finished, I would clean that up. Okay, and what would that look like?
Negative 3x to negative first. No, sorry. Negative 3 over x. Yeah, x plus c.
Okay. Change back to the denominator form when you're done with your work, but change it out of its denominator form while you're working. Okay, here's another one. So I'm going to change it out of its form so that I can do some work. All right, so it'll be 2x to what power? -1. Very good. Okay, so I need another volunteer. All right. Going to do the derivative, he said, okay? -2x to the negative 2, which would be changed back to -2 over x squared. Okay, great. Can I get a volunteer for the antiderivative? Okay, David.
C.
Just C? Why?
Because it's equals to 0.
Tell me. Walk me through it.
Okay. So
What do I do with the 2?
hold on. Okay, so 2, that's 4, so 2x
Okay, so 2x, all right, now I gotta decide what the new power is.
0
0
over,
over,
0 over,
uh-huh,
0.
0,
Is it 0? Yeah.
okay? Plus,
Plus c.
does that work? Isn't that like fundamental commandment of math 0.0? Like, you can't divide by 0?
Now what?
You give up.
Yep, that's not bad.
It works for me.
You just get rid of it. It doesn't exist.
That is somebody's derivative. It is. Whose derivative is it?
Jesus.
No.
Dang.
It's always the answer to every question. Nathan, are you thinking back there?
Huh?
Are you thinking back there?
Mine's blank.
We just had that little half sheet of paper, and there were several equations that had its derivative where x ended up in the denominator. Who's?
It's a natural law.
It is a natural log, right? It is. It's a natural log because it's somebody's derivative, and it is the derivative of something that contains a natural log because a natural log puts x in the denominator. All right. So what kind of natural log is it the antiderivative of? Okay. It is the antiderivative of 2 natural log of x.
Plus C.
Okay, plus c. And then I'm going to tell you here that every natural log, was commandment number 5. What was commandment number 5 that a bunch of you ranked as your one that you make the most mistakes on? Grammar, like which specifically here?
Oh.
Round X.
Okay, using parentheses. However, with a natural log can never be a certain kind of number. It can't be 0. What other kind of number can it never be? It can never be negative either. So you have to put absolute values anytime you do an antiderivative to protect.
Where did the 2 come from?
Where did the 2 come from?
I'm tripping.
So 2 is probably.
For the problem, yeah.
Yeah,
It's helps
the 2 came from the numerator here. It's a constant, just like the 3 came from the last problem and the 5 came from the problem before. Okay, so this is a natural log. Now, does every problem that has an x in the denominator turn into a natural log? I mean, look at your half sheet that you did for warm-up. How many different ones on the back had derivatives that had some kind of x in the bottom? A bunch of them, right? Sometimes they have x that has a square root. Sometimes, so not every x in the denominator is a natural log, but this one for sure is. Okay, how about this one? Is this a natural log?
Yeah. No. Yeah.
Does it have a square or a subtraction or anything like that? Okay, so then this would be a natural log as well. Okay, so it's antiderivative. Now, again, look at what this goes to. Look at what you're starting with. Okay, if that one is this, then what does that turn into?
The regular Y.
Regular lowercase y. And then the antiderivative of this, what does that turn into?
D2 like D2X.
Okay, no, we're doing the antiderivative right now. Okay. So what's the antiderivative of 1 over? What was the antiderivative of 2 over x? Well, that turned into 2 as a coefficient, ln absolute value x. What does this one turn into? What's its coefficient? 1, because the numerator is 1. What's its natural log? 2 plus x in absolute value. What else am I forgetting?
C.
Plus c. Okay, how would I do a derivative of that? Okay, sure, we can. What would the notation be?
D2Y.
d2y over dx. The 2 comes after the x with respect to x. Okay, how do you take the derivative of that? Bless you.
Oh, do you have to, what's it called? It's right there.
Not the quotient rule. Oh, you know what? The quotient rule would be okay. You could do the quotient rule.
Can't you put it in the like?
You could also do the power rule. What would the power on this be? 2 plus x to the what? Okay, that would be -1. So I could do the power rule, which would say move -1 to the front, then have 2 plus x to the negative 2. But you have to remember, because you have parentheses, what would you have to remember? Chain rule, which is just 1 in this situation. So the numerator would simplify to negative 1. The denominator would be 2 plus x quantity squared. So in summary, the only time that you will have natural log as your antiderivative is if you run into the problem of having 0 in the denominator. Okay, don't think that everything is a natural log. The only time you would have a natural log is if you ended up with following the normal rules for antiderivatives and you ended up with 0 in the denominator. It's a special case. So that would be the special case here, because if I tried to add 1 to that and then divided by what I got, because that equals 0, and then divided, that is a special case of a natural log. It's not every time. Okay, how about this?
Oh.
All right, Tyler, which one do you want to do?
I want to do antiderivative.
Okay,
I got negative cosine x plus c.
negative cosine x, parentheses. You are correct. The derivative is positive cosine x. Okay, so he's right. The derivative of sine is positive cosine. The antiderivative of sine is negative cosine. Okay, good job.
Hey.
Okay, how about this one? Cosecant, cotangent. It's somebody's derivative, okay? So what is it the derivative of, Isaac?
Negative cosecant.
Yeah.
Okay, negative cosecant x plus c. So in this case, it was easier to go the antiderivative route because this is already built as a derivative that we reviewed. If I was going to do the derivative route and go the other way, what rule would I need to use? I'd have to use product rule between the two of them. So it would start out as cotangent of x times negative cosecant x cotangent x plus cosecant x times negative cosecant squared of x. So in this case, it was harder to do the derivative and easier to do the antiderivative because of the way it was built. It was built as an antiderivative already. Okay? All right. Yeah. Can you hang on like 4 minutes? Yeah. Okay. We're so close to being done. Okay. We reviewed this rule earlier. This is like the e to the x and the 5 to the x. Okay. I want to do the derivative rule first. What is the rule? How many parts does it have?
3.
3 parts. What are the 3 parts? We start with 2 to the x, and then what do we do? Natural log of the base, which is 2, and then derivative of that, which is 1. Okay? All right? This is the derivative rule. So we got to think, okay, what would this be if I was doing this backwards? It's still 2 to the x, but instead of multiplying by the natural log of 2 and multiplying by the chain rule, we are going to divide by the natural log of 2 and divide by the chain rule. So it's going to start out as 2 to the x, and then we divide by the natural log of 2, and we divide by the chain rule.
What?
I don't know.
What was that?
I don't know what I touched. And then plus c.
It was like a new continent.
That looks like rock.
That was cool. Do what?
All right. Okay, how about this one? Do the reverse. So say, okay, if I was doing the derivative, it would stay e to the 5x, and then times by natural log of e, and then times by 5. That is the derivative. My antiderivative then has to start with e to the 5x, and I have to divide by the natural log of e, and then I have to divide by 5, and then add c. So always reference to yourself, what would I do if it was the derivative, and then try and do the opposite for your antiderivative. All right, this one is not a natural log. I'll just stop you right there. Even though it has x in the denominator, it's not a natural log.
Is it because
It's 10.
It's because of the square and because of the plus and because of the 1.
oh,
Okay?
I thought it was smart.
It's one of our inverse trigs. We had 3 inverse trig derivatives. We had one that looked like this.
Yeah.
We had one that looked like this. And we had one that had an absolute value in it with a square root that looked like this. Okay? There were 3. And then how did you get 3 more? Okay, you had plus or minus. These are the 3 that you have. So we should recognize and match this one. This one matches to the inverse tangent of x plus c. When would it match to the inverse cotangent? If it had a negative. Okay. How would I find the derivative?
Can you just,
I could do quotient rule,
or you could change it.
or I could do power rule. The power would be 1 plus x squared to the negative 1. So the rule would say, okay, pull the negative 1 to the front, lower the power to negative 2, but then don't forget what crucial thing when we do derivatives. Chain. And the chain rule says, you got to remember there's a 2x. That's the one that people forget for derivative. Okay. In your homework, you can go. I've got 5 more minutes, but you can go. Your homework tonight, every question is the perfect derivative of something. Everything should be recognizable. If you're looking at it and like, okay, is it a log? Is it an inverse trig? Is it a sine? It is, they're all meant to be perfect. They all have perfect antiderivatives. All right, so let's try this one. Find the solution to f prime is this. The solution is going to start with f of x as the antiderivative. If we have f prime, we can go to the antiderivative. Okay, we just do them as a section. What would the antiderivative of 2x be? Well, it would start as 2x, and then I have to increase the power from what was the original power? 1. Increase it to 2, and then divide by the increased power. The next part, cosecant squared, is the antiderivative of something perfect. What is it the antiderivative of? Cotangent, negative cotangent of x. And then you have to remember the solution has to have a plus c on the back. And then you can go back and say, okay, I can reduce the 2's and simplify it, so I just have x squared plus cotangent t of x plus c. That is called the solution.
Oh,
Okay? All right.
we're not solving.
Find all functions that satisfy dy dx equals 3x squared plus cos x. So we can change dy dx into what? Y. Okay, dy dx changes into y. We can change 3x squared into what? X cubed. It's an antiderivative. And we can change cosine x into what antiderivative?
No, positive.
Positive sine x plus c. That's the end. Okay. All right. The only time you have to go farther. Yeah. Okay. So if we have df over dt, what can we turn that into? F. If we have 1 over t, what can we turn that into? All right, let me show you the trick. Turn both of these into their powers. What do we turn 1 over t into first? T to the what? Negative 1. And then the next one will turn into t to the negative 2. Okay? What happens to t to the negative 1 when you add 1 to its power? Gets to 0. What's that a special case for? So this is the natural log of the absolute value of t minus. What happens to t to the negative 2 when you add 1 to its power? I get t to the negative 1, and what do I do with that power? Divide it. So that one's fine. That one did not require natural log. And what do I do to the 6? 6, not x. There's no x's in this problem. 6t. And then what else do I have to remember? Plus c. Now, I have one more step to go because they actually gave me numbers. Okay, they gave me this number. What do I do with it? Plug it in for all the t's. They gave me this number. What do I do to it? Plug it in where? For f. So 0 goes in for f. All the t's are 1. And what's the only thing left that I should be able to figure out what it is?
C.
C. Yeah. What is the natural log of 1? No. 0. Think about your graph of a natural log and where it crosses the x-axis. And then plus 1 and plus 6 and plus c. So what does c have to be? Negative 7, right? So my answer is f equals the natural log of the absolute value of t plus, because 2 negatives make a positive, 1 over t, plus 6t minus 7. And that's the end.